Okay, so we found the answer to that. So you can do the same with D, and you should be able to get the answer to that one. So the solutions to the questions that you are solving are actually coming just right now here. So they are doing the calculation. So if you check out the first one there, A, the answer was 1, B, the answer was 13, which is right with your answers. Me over. You have to say something? Okay. And if you check out C, they found 2.87, which is exactly what you guys have calculated. Therefore, you should be proud of yourselves and know that you're actually grasping the concepts that are required of you in this particular run. So D, that is the answer that will be expected of you to find. So please work out that particular expression. Otherwise, if you find difficulties, you can inbox and I'll be able to shed more light. That's tomorrow. Okay. So we go to acid-base neutralization reaction. All right. So a neutralization reaction is a reaction that happens between an acid and a base, and a salt and water is a resultant of this reaction. So an acid reacts with a base to form salt and water. When this happens, we call that as a neutralization reaction. We have 3 types of neutralization reactions. We have the first type that produces a neutral salt. When a neutral salt is produced, that simply means a strong acid reacted with a strong base to form a neutral salt and water. An example there is given. Sodium hydroxide reacting with, yes, given.
Sorry, can you show that slide shows the solution for D? I didn't capture it.
Okay. So your answer to D is actually 11.66. Okay.
Okay, thank you.
All right. And then where we are here, we have a neutral salt, and then we have an acidic salt. So an acidic salt is produced when a strong acid reacts with a weak base. Okay, so you're going to have an acidic salt plus water. An example, HCl, a strong acid, is reacting with ammonia, a weak base, to produce ammonium chloride. So this is an acidic salt. Okay. And then you have a basic salt when a weak acid reacts with a strong acid, strong base to produce a basic salt. Now, each one of these salts has a certain behavior that it portrays when it is dissolved in what? In water. When a weak acid that produces an acidic salt is dissolved in water, it is going to produce a basic solution. When a basic salt is dissolved in water, it's going to produce an acidic solution. So please, you should be able to remember this. Hydrolysis of acids and bases. So here they are telling you what happens when a neutral salt is dissolved in water. It produces a neutral pH. When an acidic salt is dissolved in water, it produces a pH which is less than 7. When a basic salt is dissolved in water, it produces a pH which is greater than 7. In case 2, pH is due to the hydrolysis of the cation. All right. So what you're going to have is, for example, you have an acidic salt. Let me just take you back to an acidic salt. So this is the acidic salt that you have, ammonium chloride. So what is happening here is that if you look at the ammonia itself, this ammonium ion is a conjugate, and this ammonium ion is a conjugate acid. So when a conjugate acid behaves as the starting material, it becomes the acid itself. because what is going to happen is that this is going to be losing a proton. Okay, so when this dissociates in solution, NH4 dissociates this salt, NH4Cl. When you write the dissociation of this, you're going to have NH4 plus Cl minus. Now, Cl is coming from the strong acid and therefore cannot dissociate, but NH4 minus can dissociate. So when you pick up the NH4 minus and you write its dissociation, what you're actually going to get is NH4 plus dissociates to give you NH3 plus a proton, which is H plus. Because it is producing H plus in solution, that's why we are saying it is producing a acidic solution. That's why here they are saying when this salt is dissociated in water, what it produces has a pH that is less than 7. It is because of the presence of the what? Hydronium ion that it produces in solution. The same is true when you look at the dissociation of a basic salt. It is going to produce hydroxide ions in solution. So this is what just these two cases are trying to explain. Some of these things would be very easy if at all we were to actually have somewhere where I can write something for you to see. But anyhow, I hope when I'm explaining, you guys are trying to write up something so that you see, okay, actually, this is what I'm talking about here. So hydrolysis of an acidic salt. You have ammonium chloride. It dissociates into NH4 and Cl, 100% dissociation. Now, since Cl is not hydrolyzed as it comes from a strong acid, HCl, therefore only this is going to be hydrolyzed, NH4 plus. So NH4 plus in water gives you NH3, which is a conjugate base, plus the hydronium ion H3O plus. So because of the presence of this salt is said to produce a pH that is less than 7. Now look at what I was telling you. This one, since it is losing a proton, we consider it to be an acid. What it produces is a conjugate base. The same is true for the other expression where you are looking at the dissociation of a basic salt. Then here they're asking us to do a calculation. Calculate the pH of a 0.1 molar ammonium chloride solution. So for you to calculate the pH of this, you dissociate this. When this dissociates, look at what is happening here. This dissociates. Now, we have already seen that the first dissociation where ammonium ion and the chloride ion are produced, nothing happens. Therefore, we do not consider that. What we just consider is the dissociation of the ammonium ion. That's why in the dissociation, we have the ammonium ion and water dissociating to ammonia and the hydronium ion, all right? Since this is a weak dissociation, the ICE table shows us that X is equals to, so when you do the ICE table, initial, change, equilibrium, what you're going to find is that this is complete, this is a weak acid, okay? Since this is a weak acid, it partially dissociates to these. Since it partially dissociates, if you check what we did calculate earlier, this below here, you're going to put on the ICE table, below this, you're putting 0.1, and here you're putting 0, and here you're putting 0. On the change, you have minus X, here you have plus X, and there you have plus X. And then when it comes to equilibrium, you're going to have 0.1 minus X, and here you're going to have X, and there you're going to have X. Then when you write your Ka, so Ka is equals to this, the concentration of the ammonium and the concentration of the hydronium ion. Now, look at what you've been given here. You've been given Kb instead of what? Ka. So since you've been given Kb, you have to convert Kb into Ka. And if you remember, I gave you an expression that associates Ka and Kb. This is this equation here. So Ka is equals to W divided by Kb. Now, Kw is 10 to the power negative 14. I gave you this one earlier. So divided by 1.8 times 10 to the power 5, which gives you 5.56 times 10 to the power 10. So this is your Ka now. So this Ka can now be placed in your equation, and you can be able to calculate the value of X. When you find the value of X, which is this one here, you can now say pH is equals to the negative log of the answer you get, because the answer you get, X, is the same as the concentration of this ion, and therefore you are finding that the answer is 5.13. Anyone behind on how this has been calculated?
It's clear, sir.
All right. So here they are doing a basic sort. So this is a weak base. It dissociates to give you this and this, just like we did earlier. Now look at what you've been given here. You've been given Ka, but look at what you have in solution. You have the hydroxide. So when you have the hydroxide in dissociation, meaning you are using Kb. Since this is a base, so you use Kb. After the dissociation, look at what you have on your right. You have Kb. So Kb, therefore, is what we're going to use for the dissociation. Therefore, we have to find what value of Kb we have. So using Ka, we can find Kb. This is how Kb has been calculated. And then you find the value of X. The value of X is equals to the value of the hydroxide ion there. And therefore, you can find the negative log of this as pH is equals to 14 minus POH. After you have found what POH is, this is the answer you are getting. I think these things are straightforward, isn't it?
Yes.
Yes.
Okay, so we have buffer systems. Okay, so a buffer is defined as a solution that is able, or a solution that is made from a strong acid and a weak base, or a weak base, a weak acid and a strong base that resist change in pH. A buffer is a solution made from a strong acid and a weak base, or a strong base and a weak acid that resists change in pH. That's what a buffer is. Now, the extent to which a buffer resists change in pH is known as the buffer capacity. So the buffer capacity is the extent to which a buffer solution resists a change in pH, and this has a value of plus or minus 1. So the buffer capacity of any given buffer is plus or minus 1. Now, we have two types of buffers. That is an acidic buffer and an alkaline buffer. An alkaline, which can also be referred to as a basic buffer. An acidic buffer is formed between a weak acid solution and a strong base. All right, that is what is going to give you a weak acid, a basic, an acidic buffer. An alkaline buffer is formed between a weak base and a strong acid. All right, so this gives you an acidic salt, this gives you a basic salt. Anyway, we've already looked at this. So the buffer action is the property of resisting a change in pH when a strong acid or a strong base is introduced in a buffer solution. That is buffer action. Methods of calculating pH of a buffer solution. We have the ICE table and we have the Anderson-Hasselbalch equation. All right. So we have the Anderson and the Hasselbalch equation. The the ICE table method, I think we've looked at that one when we were looking at acid bases. There's no difference with what we are from doing. Then the HH equation is actually a derivative of the ICE table equation. So when you have the concentration of a buffer, when you have this, okay, which gives you that, this is just the concentration of a weak acid, which is equals to M of the weak acid, V of a weak acid divided by V of an acid plus V of a salt. This is how you find this concentration. Okay, so this is volume of the acid, molar concentration of the acid, then the volume of the acid plus that of the salt. Then the salt is equals to mass of the salt, volume of the salt divided by, so if you check out this, number of moles is equals to mass times volume for concentration. So concentration times volume gives you the number of moles. Concentration times volume gives you the number of moles. If you divide the number of moles by total volume, what you get is the concentration. That's just what this is representing here. Nothing difficult or something you've not seen, no. Okay, so the Anderson-Hasselbalch equation of an acidic buffer. So when you do from here, when you have this, when you introduce the negative log to this is what you get. All right, so negative log of this and then the negative log of this breaks down, and then this is what you're going to get at the end of the day. So pH is equals to the negative log of Ka plus log of A, which is a conjugate when this dissociates. All right, when this dissociates. So this is an acid dissociating here. The acid dissociates to this and that. So if you check out, we have this, which is this one divided by the acid itself. Now, negative log of Ka is the same as pKa. Therefore, instead of writing it like this, you can say pH is equals to pKa plus the log of the conjugate divided by the acid. If this were to be a base, pH is going to be equals to pKb plus the log of conjugate divided by base. That is how you calculate using the HH equation. pKa is equals to the negative log of that, and then pKb is equals to the negative log of that. So the maximum buffer capacity of a buffer, that is that. They're explaining what I've already talked about. So basic buffer, I think this is what I'm just from explaining. Instead of Ka here, you're using Kb. This is the only difference that is there. And then example 1, use the ICE table. So when you're using the ICE table, what you should understand is this. When, let me see the question. Suppose you have a solution which is 0.5 molar in acetic acid and 0.1 molar in sodium acetate. So you've already been given the concentration of the acid and the concentration of the conjugate. What will be the pH of this solution? So they've given you Ka. You have this dissociating into this and that. Okay, so sodium acetate. This is a sodium acetate. This is acetic acid. The buffer itself is a sodium acid. It's an acetate buffer. That's why we are dissociating a what? Acetate here. So you have that dissociation, and then you have this is the sodium acetate dissociation, and this here is the acetic acid dissociation. Now, this is a salt, sodium acetate. Since it is a salt, it will completely dissociate in solution. Okay, since it completely dissociates, this simply means that all this concentration is for the acetate. This is 0.2, H you do not have, but this you have in solution as 0.1. The change is minus X, then here plus X and plus X. Then minus X, X and 0.1 plus X. Check at the Ka value. Ka value is greater than 4, meaning it's negligible. That simply means this is going to be equals to 0.2 and this is going to be equals to 0.1. You continue with your calculation. Therefore, Ka is equals to X, 0.1 plus X divided by that. They've said here X is very small than 0.1 molar and 0.2 molar. Therefore, we just consider these values. That's what this here means. So Ka is equals to 0.1 X divided by 0.2. So X is therefore equals to Ka, and you already have the Ka and you have this. So when you do your calculation, you find the value for the concentration of the hydronium ion. Now, this is what you use in the pH calculation. Therefore, pH is equals to the negative log of the concentration of the hydrogen ion. This is the concentration of the hydronium ion. When you place it there, you find your answer to be 4.44. So this is how they are arriving at this answer. Is anyone behind anywhere? Anyone behind?
We are following, sir.
Okay. Now, this is when you use the ICE table. If you don't use the ICE table, you can use the HH equation. The HH equation is pH is equals to pKa plus the log of the salt divided by the acid. So what you're going to do, find pKa, okay? Find pKa. The first thing, write the equation. After you've written the equation, find pKa from Ka. So pKa, find what value it is giving you. What is pKa of this value here? So what is the negative log of 1.8 times 10 to the power negative 5? Find for me. What answer do you have? Negative log of, yes?
$4.74.
Okay, so that is your what? That is your pKa. So now replace in the HH equation. pH is equals to that value that you find for pKa, 4 point, whatever value it is, plus the log of the concentration of the salt, which is 0.1, divided by the concentration of the acid, which is 0.2. Calculate and tell me the answer that you're getting.
$24.2.
When you do your calculation, that's the answer you're getting. You have pH is equals to pKa plus the log of salt, concentration of salt divided by concentration of acid. Now, You are just from calculating pKa, which is 4.7 something you've told me. So right now, pH is equals to that value that you're from finding for pKa, 4.7 something plus the log of, they've told us that sodium acetate is 0.1. So you're going to have the log of 0.1 divided by 0.2 because it is salt over acid. When you do 0.1 divided by 0.2, what answer do you have? Then that answer, do the log of that answer. What are you getting to? Then the answer that you're finding from there, you're going to say plus the pKa value, which is 4.7 something. Then tell me the answer that you get. That's how you calculate that one. Yo, guys, what answer are you getting? Be quick. What answer are you getting, you guys?
Me, you lost me on the figures. No lie.
No, I can't lose you on your figures. If you have the equation, you should be in a position where you place in the values yourself. That's the all aspect of, yeah, you have the values, you have the equation. So what pKa you've calculated, put it there. Log, concentration of the acid, the salt. You have in the question the concentration of the salt. If I take you back to the question, here is the concentration of the salt. This one here. Sodium acetate, the salt, this is the concentration. The acid, this is the concentration. So just place these values in the equation and then calculate.
Okay, just run us through again the whole process.
pH is equals to pKa plus the log of the salt divided by the acid. So these are concentrations this side, okay? pKa you do not have. What you have is Ka. That's why I said first calculate for what? pKa. So pKa is equals to the negative log of the negative log of Ka. So therefore, the negative log of 1.8 times 10 to the power negative 5. And one of you, I think that should have been Muzira. She said the answer is 4.7 something. That is your what? pKa value. So when you go back to the equation that you have now, pH is equals to, where there is pKa, place in this value are from calculating, which is 7 point something, plus the log. On top there, put the concentration of the what? The salt, which is 0.1, divided by, put the concentration of the what? Acid, which is 0.2. So when you start calculating there, don't place everything at once. No, start by working on the far right. 0.1 divided by 2. What answer do you have? Whatever answer you get, do the log of that answer. Just place log answer. It is going to give you the answer. Then to that answer, just say plus that value that you found for the pKa, it arrives definitely on the answer of this particular question. If you were following me right now, you should be at the answer. What answer have you gotten?
4.44.
Exactly. So irrespective of the method that you use the ICE method. So the ICE method is just that the ICE method is a bit longer, where you have to do this table, put in all these values, and then come and make assumptions. Like in the second step here, they're making assumptions and stuff before arriving at the answer. When you use the HH equation, it's straightforward. The only calculation that you have outside the main HH equation is the what? pKa calculation. Once you do the pKa calculation, place it in and run the calculation. So if they've not specified the method of use the Anderson-Hassenbeck equation, because it is a straightforward equation that gives you the answer directly with simplicity. The marks will be the same, whether you go by the ICE table or you go by the Anderson-Hassenbeck equation. The marks are going to be the same so long as they don't specify. But if they specify like they have in this particular example, you have to go by that particular method. That's why they've given this method first, and then they have come and used the HH equation. This is what I'm just from explaining to you. So they've used this equation to do the calculation, and they found that it's 4.4. So irrespective of which method you use, the answer is always the same. So that one was straightforward. Usually what they're going to ask you is this: calculate the pH after 0.01 moles of gaseous HCl is added to 20 mL of each of the following solutions. So 0.5 ammonia and 1.5 ammonium chloride. They've given you the Kb for ammonia there. And then you have, so this one again, you have to come up with, you are not interested in this dissociation, you are interested in the dissociation of this, or you can use pKb, okay? So what it is here is that you can use the ammonia going to that. So since this is what you have, ammonium chloride and the hydroxide here, therefore POH is equals to the negative log of Kb plus the log of the salt over the base. So look at what you have here. This is the base. So this is the concentration of the base, and this is the concentration of the salt. So this is the salt. So when it comes to this equation here, on top, you're going to put the concentration of the salt, which is this. Below, you're going to put the concentration of the base, which is this. And then you only have to find pKb. What is your pKb value? So POH is equals to that. So pKb, you replace, you find this. But what you've calculated for is POH. What do you want? pH. What is the relationship between pH and POH? This is just where you subtract from 14 this value, and it gives you this as the what? The value you have. This is before you add 0.1 molar of the what? HCl. What you've just calculated is the pH of the buffer. So this buffer solution has this pH. Now, when this amount of acid is added, what it actually does is that this acid is going to reduce the number of moles, or it is going to reduce the concentration of the what? This base, and it is going to increase the concentration of the salt. So when you add an acid to a basic buffer, it reduces the amount of the acid, and the amount of the base, and increases the amount of the salt by that same amount. So simply meaning, to this amount in the HH equation, this equation, you're going to add on the salt 0.01, and then on the acid, you're going to subtract by 0.01. This is what they're showing here. So you've been given the volume of the salt. Find the number of moles that you have of each one of these. Each one of these two, they've given us this. So how many moles of ammonia are in this volume? How many moles of this are in this volume? When you find the number of moles, to the number of moles of ammonia, subtract this. To the number of moles of the salt, add this, and then find the new volume. Or since the volume is going to be the same, actually, in this case, you don't even need to find the new volume. You just need to work with the new answers that you get. So this is what they are doing here. So the HCl will reduce the concentration of ammonia and increase the concentration of the salt. So this is what is happening. These are the number of moles. These are the number of moles. HCl is that. You have that. So this is reducing when you do the subtraction. This is increasing when you do this, the addition. And after that, you calculate by just placing into this the value, and you find that. And when you subtract that, you're going to have this as the new pH. Is that clear? Then I think when we meet tomorrow, we're just going to run through the titration part that has remained, and then we can go to answering the tutorial sheet under acid-base equilibria, unless you have questions. Okay,
So I'm kindly asking for the notes.
Okay, so I think we will send this tomorrow when we are done with the component we are doing. So the notes will come at the end of the learning, the lessons.
Because I missed yesterday's tutorial and it was just quite hard for me to catch up today. So maybe I thought maybe I would go through the work after being done yesterday so that I can connect